record on this computer. There we go. Now we're rolling. Okay, so I did post in, where are we? As you learn, 3.5 linear approximation notes. So there's notes there. There's a blank practice sheet. And then this morning it occurred to me that I didn't post the answers to those. So I posted, I mean, it's just examples. It's examples using a trig function. It's examples using a cube root function. But you basically do this linear approximation formula with the value that's indicated, and you come up with an equation of a line. And sometimes the line is nice, and sometimes it has pi's and e's and other things in it. But it's approximating, which, you know, if you have the real thing, why approximate? But this is a concept that's in this course that you're going to look at. But so there's notes posted, and that's the one that I said just look over them, try them, see if you have questions on your homework. I don't really think there was a ton on here. The 4-2 guided learning, is it this one? Some of you, depending on, is it the guided learning? It has the weird one. So yeah, if you are the lucky one that gets, it's like an 8 on the x to the 5th and a 15. Apparently, I'm told by the sapling guy, our contact, there's a coding wrong on one of the versions of the question that it spits out in cycles, iteration, whatever you want to call it. So they're working to fix that. So if you, and this looks super nasty, you don't have to enter it like that. If you get to these and are having trouble doing the minimum and maximum for this particular very first guided learning question, reach out to me. You may have it wrong, but you may be the lucky one that got the one that was coded weird. So, and you get a bunch of tries. So if you get to try 9, you might want to reach out and be like, am I doing this right? Am I doing the wrong one? But so this one's really short. And then there's a 4-3 guided learning, which I think we should get into today. And I posted some of the homework. Again, the homework deadlines, I mean, they could change, but you should be able to get the 3-5 done by I think, is that Friday? What is today? Oh, that's tomorrow. The guided learning for 3-5. The homework by Friday. The guided learning here by Friday. I mean, you have to work. I mean, I'm not going to leave it open for 2 weeks because then a lot of you will drag your feet and you won't do it for 2 weeks, and we don't need that. So pay attention, get it done as quick as you can. The 4-2 homework, I think that's what we looked at yesterday. Most of those questions are just find the critical numbers or find the absolute min and max on a given interval. I think that's like the bulk of those questions in that section. So we can look at a few more examples of that today if you want to. Homework 8, I don't know if you can see this, it's kind of, can I zoom in? There we go. It does put 3 sections together. And if you notice, it skips 4.5. We're gonna cycle back here after next week and do 4.5. It's separate. But 4-3, 4-4, and 4-6 all use first and second derivatives to come up with information about a function. Where does it increase? Where does it decrease? Where's the minimum? Where's the maximum? Where is it concave up? Where is it so I put all of that homework together because those topics go together. So that's up there with a due date. That'll probably change. But for now, what's up there, take it as that's when you're expected to do it. And I mean, unless you took on a job that works hours and hours and hours a day, you should be able to put some time into this course that you may not have been able to before with all of the other distractions of Appalachian State. Because you don't have them because you can't go around people. So I'm going to stop this and switch back to iPad. We'll have to play around to see about people sharing their screens. I think you're supposed to be able to share your screen with me, but that may be more of an office hour thing, which I still am holding, by the way, but I have had nobody show up to it yet. Okay, so yesterday we looked at this concept of a local versus an absolute minimum and maximum. And I mean, I don't think, unless it's in the guided learning, there's not a lot of local versus absolute in the homework. I think it's mostly absolute and critical numbers. But remember, absolute looks somewhere specific, and somewhere it has a high and somewhere it has a low, and you should be able to find those. The local is more fluid and you can move the interval around. So, you know, like, let me pull this little pointer here. Here at this X2 peak, you could go to the left and to the right and fix some interval and be like, oh, hey, there's a maximum. And then you can move it down here around X3 and like, oh, there's a minimum. So that's what the local, and it didn't include endpoints for local, but for the absolute, most of the questions have you look, it gives you a function and it tells you somewhere on the function to look. When we move into section 4.3, they'll be more local, but we'll be looking in between certain intervals. So the biggest thing that you have to do really in 4.2 is to be able to find the derivative and where the derivative is 0. So I didn't know if anybody had specific questions, because I think we do this one yesterday? I think we did this one yesterday. Maybe. I feel like we did one of these. X cubed, we found the derivative, we factored it, we found the critical numbers, but we were only looking from 0 to 2, so we didn't count the 3. And then we used the critical numbers and the endpoint to figure out where was the biggest number and where was the lowest. And on your homework, and even when you answer, when it says to find the absolute maximum, it's wanting the y value. And the absolute minimum, it's wanting the y value or the output from the function. It doesn't want the input, it doesn't want the point. Unless it asks you for the point, it actually wants the x and the y value. And so, like I said, on a lot of the homework, I don't remember which ones we did yesterday because I feel like these are old notes. On the homework, there's product rule, there's quotient rule, there's trig functions. I mean, there's all the functions that we could have done before. They're here. There's natural log, there's power, chain, all of those. So I guess, does anybody have a question that they've tried that they want to look at that involves finding the absolute on an interval? Did anybody try those to, maybe you're still on 3.5, I don't know. I mean, I have a few that I could still do. I could give you the opportunity if you'd like to ask. Anybody? Haven't gotten there yet, still adjusting to the shock of being online and in your house confined. Yeah, maybe. Okay, well, I mean, I can do another one and then we can look for examples. I got some piecewise examples because I think those are on there too on your homework. So if we were doing, not a red pen, how about find absolute max and min for this function. So let's say we do the function x squared over x minus 1 on the closed interval -1 to 1/2. So this is a rational function. It has a vertical asymptote at 1, even though that's not really important for this interval. But if we want to find the absolute max and min, we have to first find the critical numbers, which again, that's where the derivative is either 0 or where the derivative is undefined. In this case, we're going to have something where it's undefined because it's a rational function. So find the critical numbers and then you use the critical numbers. So use the critical numbers and those endpoints in the actual function to determine which one produced the biggest number and which one produced the lowest number. So first thing we need to do is find the critical numbers of the derivative. So this is a quotient. So we get to use quotient rule. And again, if I lose you, you stop me because it doesn't really, I wish it like did this little chime if you chatted, but I don't think it does. Can I make it chime if you chat? Nope. Okay. So if you chat and I don't see it, just give me a second to look up and it'll flash orange. So this is quotient rule. So we'll use quotient rule. So the derivative, that doesn't say rule. The derivative of the top is 2x times the bottom minus the derivative of the bottom times the top all over the bottom function squared. So again, this is why it's extremely important that you understand how to algebraically clean up the function. because anytime it's rational, you have to consider what makes the numerator 0 and what makes the denominator undefined. Those are going to give you critical numbers. So here, we're just cleaning up as much as we can. Like distribute 2x squared minus 2x minus x squared. So that's what, x squared minus 2x over x minus 1 squared. That's your derivative. And to get critical numbers, you need to find where this whole derivative equals 0 or is undefined. Again, because, I mean, if it were a polynomial, you would just factor it. Maybe quadratic formula is a tool that you can use. Square roots, I mean, all those solving methods that you have. But if it's a rational function, the rational function is going to focus on what makes the top 0, and then separately what makes the bottom 0, because that's where the function will be undefined. So for the top part, x squared minus 2x equals 0. If I factor an x out, if you need to, you can use the quadratic formula, but there's an x squared, there's a 2x, I can pull an x out, and then I can set each one equal to 0. So I get 0 and 2. And then if you focus on the bottom here, x equals 1, the function is undefined. And it's not in the original functions domain. So we won't consider it for a critical number. And I feel like I might have mentioned that yesterday, but in order for it to be a critical number, it has to actually be in the domain of the original function. And since 1 is not in the original domain, when we find it as a critical number, we just don't use it as, like, it's not going to be, there's of no importance. I mean, there's an asymptote there for this particular function. So we have a 0. We found a critical number of 2, 0 and a 2. And now we want to sort of focus our thoughts on finding extrema in this interval from -1 to 1/2. So I might have to come over here to the side because I feel like I ran out of room. So if we wanted to look on this closed interval of -1 to 1/2, you have to consider the endpoints and then also your critical numbers. 0 is in the interval -1 to 1/2, so we will use it in our algebra, but 2 is not in this indicated -1 to 1/2 interval, so we won't use it here. We'll use it in the next section, but in order to find an absolute min or max here, we won't use it because it's not within that range. And we have some chats. Critical numbers are chosen. Okay, so Tori's answer. Okay, Brianna, so we'll use, so you can't use a critical number if it's not in the domain of the original question, of the original function. So up here for the original function, x couldn't be 1 to begin with. So it's not considered a critical number if it's not in the domain of the original function. That's like a, I don't know if I wrote that anywhere or not, because we hadn't really come into any domain issues. I don't think I had. But that's sort of like anytime we get into these quotients, it's only a critical number if it's in the domain of the original function. Otherwise, it's not going to be considered with these functions. Plus, in this particular case, 1 is also not within that interval, so we wouldn't use it anyway for this problem in particular. They may be useful in the next, I think, section 3 and 4. But as far as finding absolute min and max, it's not in the interval we're looking at for this one, and then it's also not in the domain of the function. Okay, so we're not using 2 right now, even though we found it to be a critical number. Let me pull some red. So we're not going to use the 2 right now. So we're only going to use 0 and then our endpoints. So when we go back and do the second part, in order to find the high and the low, you evaluate the function, let me make that a little bigger. Evaluate the function at the critical number that we were using, which was what, 0? Yeah, 0. And then we'll evaluate the function at the endpoints. So this one was from critical number. This was an endpoint. 1/2 was an endpoint. And again, they're going back into the original function. So however you want to use function input, you want to use Desmos, whatever. If you plug 0 into that equation, 0 squared over 0, it's 0. If you plug in -1, I think you get, what is that, -1? I think you get -1/2 if you plug in -1. And if you plug in a half, again, calculator it up, 1/2 squared over 1/2 minus 1, I think you get -1/2 again. For that, I mean, this is where you should be able to plug numbers into a function at this point in your mathematical career. So we only really have 2 output values. 0 is the highest, so it's your max, and -1/2, even though it's there twice, that's your minimum. So if it asked you for the absolute minimum, you would say -1/2, and if it asked you for the absolute maximum, you would just say 0. Okay. All of those other critical numbers were not used for this particular example. Okay. Questions on that one? So you got to find the derivative, find where it equals 0, and then use those critical numbers, the useful ones, back in the function to find your min and your max. And I mean, your homework is full of these. There's, I don't even know, I had a couple more. Like I said, if you want to ask, feel free. Like I have one with the square root. I don't know if you want to, I think it was on your homework too. It said, find the absolute max and the absolute min for this function. 4 minus the square root of x from 0 to 4. Okay, so you've got the square root function. It's been like reflected and moved, and you can graph it if you want, but we're only focusing on the window from 0 to 4. So those are the endpoints that we'll consider. The domain of the function is everything that's positive, as long as it's a 0 or higher, because it's just a square root. So you can square root 0, 0 is not a problem. If we do the derivative, so the derivative of 0 is, 4 is 0. X to the square root of x is like x to the 1/2. So if I write it like that, we can use power rule. So we've got -1/2 x to the -1/2, or -1/2 with the square root of x. So the only critical number that comes out of this one, nothing will make the top 0. So there's no critical numbers from the numerator, because it's a 1. You're not going to make a 1, 0. So that happens. It's fine. The denominator, the critical number that you'll get here, is going to be 0, because that makes the bottom undefined. And it's considered a critical number because it is in the domain of the original function. So we can use it, but it also happens to be the endpoint, which is fine. So we only have 2 numbers that we're looking at doing the high or low. One's going to be high, one's going to be low. So when we test these and we do f of 0 and f of 4, if you plug in 0, 4 minus the square root of 0, you get 4. And if you plug in 4, 4 minus the square root of 4, was that 2? Yeah. So 4 is your absolute max, 2 is your absolute min. That's all you have to do for those. And it's the y value that you answer for what's the min and what's the max. Some of the questions just ask you for the critical numbers. Some of the questions ask you to identify the absolute max and the min. But the hardest part will be finding where the derivative is 0. I think that's what a lot of you are going to struggle with, just because of the last derivative chapter. Okay. So critical numbers, again, come from where the function is 0 or undefined. And then if you are doing absolute extrema, you have to test the endpoints, make sure that your critical number lives within the range that you're looking, and then make sure that the critical number is in the domain of the actual function. Trying to think. We're good. We're good. Unless you have specific ones. Like I said, if you've started the homework for 4-2, maybe you have some. If you haven't, bring them tomorrow or email me about them, or we'll set up a session later. Like I said, my kids usually bathe around like 7 or 8, and then they just chill and watch TV. So if we need to log online, we can. If you need to do the math lab, it's open 4 to 7. If you need to do the late night tutoring, I don't know if it's running, but we can check. I can check it out. I haven't heard that it's not. Anybody have a question on any of them? You guys are so quiet and I can't see your faces to see your expressions. Okay, I'm just gonna keep going. Something else that I did upload were notes on, I think there's some piecewise questions in your homework. I'm pretty sure, I'm about to go look before I spend 5 minutes doing this example, but I'm pretty sure there was a piecewise on, let me go back and share this. Maybe share, maybe not share. 4.2 homework, here we go. We're good, we're good still. Okay, 3 of you have started this homework. All right, so if we click through the homework, for those of you that have not, so we have absolute min and max, quadratic, there's a square root, there's a piecewise. Okay, so the critical number on the piecewise is what I wanted to make sure that we talked about, because I don't really think, those don't really give you anything. No, there's a product rule, there's a trig one. No, I think those were the only ones. So you may just be doing critical numbers. And if that's the case, that's all I'm about to do with you. I posted some notes on them on As You Learn already. Yeah, so we'll do one. We'll do a critical number one with a piecewise so you can understand how those apply. Let me go back to sharing. All right, so piecewise function. I don't really know that one is easier than the other. No, okay. So here we can look at absolute min and max too, but looking for critical numbers for a piecewise. We've done piecewise functions some before. So understanding how to graph it is helpful, understanding how to, I think differentiability came into question. So again, critical numbers are where the derivative equals 0, or, and this is the really important part for this, the derivative is undefined. And if it's undefined, that means it's a value where it's not going to be differentiable. And you remember we had those, it can be continuous, but if it created a sharp corner or any kind of a cusp, you couldn't take the derivative of it. The function exists there. Okay. The function exists there, but you couldn't take the derivative of it, so technically the derivative is undefined there. So if we consider this piecewise, let me try that one again. So 2x minus 1, but only between 0 and 2, and then an x squared minus 5x plus 9, but only between 2 and 3. So it's like a little piece of a line and a little piece of a parabola. And we can, I mean, we can look at the graph if you want to. But I think, just so you know, this is what it looks like. At 0, it's down here at -1. And then, I said you could graph it if you want to, but 2, 3. I did this earlier. So at 2, it's up at 3. So it makes the straight line to here. And then the second piece fills in, I don't know that pink's much of a different color. The second line fills in with this little parabola that does that. If you want to graph it, you can, but that's what the graph ends up looking like. So it's continuous everywhere. So that's not really a question. Here at x equals 2, it has that cusp where the limit from the left and the limit from the right, like the slope of their tangent lines aren't the same. It's continuous, but it doesn't have a derivative there. So this 2 is going to be critical. But as far as any other values that can make it 0, if you want to find critical numbers, the derivative you would consider in pieces. So the derivative of the top 2x minus 1 is just 2, and the derivative of the bottom is 2x minus 5. Okay, so for that, you have to consider what would make the left piece derivative 0, and nothing would. So there's no critical number for here. And then what would make from the right 0, like the right piece of the function, what would make that derivative 0? Because again, that's what's a critical number, is what makes it 0. So for this one, if you set that derivative equal to 0, you get what, 2x equals 5. So 5 halves, or 2.5, right? Okay, and do you see what happens at 2.5 on this picture? If I drew it correctly, according to 2.5 is right about here. Do you see how we have a local minimum there? So it'll be a critical number, especially when we move into section 4.3. But for right now, it's not the absolute, because you can see on this picture that I drew, it's not necessarily the lowest part of the graph, but if we locally move around our interval, that's a local min, which you're not asked about in homework, but it's worth mentioning because, oh, that's a huge eraser. Back off of that guy. Okay. So 5 halves is a critical number. It's in the domain of the original function, so that's considered a critical number. We have our, I didn't give you any endpoints. We're looking, well, we'll look at endpoints in a minute. But as far as the function goes, 5 halves is the only thing that makes the derivative 0. The other thing that you have to consider with a piecewise function is there anywhere where the derivative is not defined? So for this piecewise, especially if it has continuous pieces, which this one does, you need to consider the break, that's what I'm going to call it, the break in the domain of the pieces, because if you have a break in the graph and it's not differentiable, then that's going to be important for a critical number and you might miss it on your homework. So for this one, and when I say break, this is what I mean. You had this line 2x minus 1 from 0 to 2, and the domain split at 2. And from 2 to 3, you had a totally different function. So when I say the break in the domain, I'm having you look at this break in the pieces. So 2 was the split, and on the picture you can see that, I mean, it's continuous. That's not the question here. The problem is when you come from the left and when you come from the right, the derivative pieces at 2 are different. And that makes it not differentiable, and that makes the derivative undefined. So not only do you have to take the derivative of the pieces and see what could make them 0, you also have to consider at the x value of 2, if you look at the derivative, if you look at the derivative of 2 from, I'm going to put this little minus sign, so the left piece versus the derivative of 2 from the right piece, with these little, I think some of you have seen these before with like left and right hand limits. And again, the left and the right piece I'm doing from these. Oh, not that one, maybe this piece. Okay, so if I do the value of the derivative, which is the slope of the left piece, the slope there is 2. Like I don't have anything to plug in, so the answer is just this 2. If you do the derivative of this right piece, let's look in here, then it's 2 times 2 minus 5, and you get, what, -1? So these slopes are not equal. The derivative, or not really derivative, let me erase that, sorry. So it's not differentiable here, and we've had this before in another chapter. So an x value of 2 is going to be a critical number because it is a place where, I'm writing a whole lot, sorry, the derivative is not defined. So it makes it a critical number because it's a split in the domain, and it creates a point that's not differentiable. So being not able to take the derivative makes the derivative not exist, if that remotely even makes sense at all. There's only a few piecewise functions, so it's not the end of the world if you have trouble with them, but just know that they're on there, and that's what you have to do. If you have to find the critical numbers, consider what makes the derivative pieces 0, and then consider the split in the actual function itself. Okay. Anybody have a question on that one? I'd let you try them. I have another example I could do tomorrow if that would, again, I don't know. Oh, anybody? Any takers?
Can you scroll up a little bit?
Like this?
I guess I meant, okay, there we go.
So you see the bottom?
Yeah, I couldn't see it on my screen.
That's okay.
I was wondering why, if there was a specific reason you chose 2 to check as, to see if it was undefined.
Yes. That is where I can zoom out. In the original piecewise function, this guy.
Mm-hmm. Oh, okay.
2 is where it's split. 2 is where the pieces split.
Okay, yeah.
Yeah.
Thank you.
Yeah. So again, wherever it splits, sometimes they come together seamlessly for continuity, but we talked about differentiability. I feel like that was like chapter 2, maybe?
Mm-hmm.
The beginning of chapter 3. If they come together at a sharpness, or if they're like this, it's not continuous. But if they come together continuously, but it's a sharp point where the slopes don't match for tangent lines, the derivative won't exist there, and you can't do it.
Okay, thanks.
Mm-hmm. Anybody else? Again, you take the derivative of the pieces, you find anything that would make them 0 for critical numbers. Let's try to see if I had 0, 1. I have another one. It's not the, not that. Like this piecewise function. Oh, that's really green. Try that again. So say you had this one. We've got x squared from 0 to 1, and then 1 minus x squared from 1 to 2. Okay? So we're only looking from 0 to 2. That's where we're looking for. This is defined from 0 to 2. So 1's a parabola, and I don't even know how these two would come together. You could graph it if you wanted to see it. Here, I'll graph it. Why not? X squared. Oh, how did you have to do this in here? Braces? Gosh, it's been a long time since I did this. 0 less than or equal to x less than 1. Is that graphing correctly? There we go. There's our little guy with the weird scale. Okay. And then the other one was 1 minus x squared, but I only need the piece from 1 to 2. Look at that. Well, I can tell you right now that the 1 is the problem. There's a break in the graph at 1. It's not differentiable at 1. It's defined at 1, but it's going to be a critical number because the derivative doesn't exist there. So even though it's not continuous, 1 is still considered a critical number. And if I were looking at a 0 to 2, that may be the only one that we come up with anyway. Let's see. Let's go here. So again, visually, the split is at 1. That's definitely a highlighter. So if we look at the derivative, because we want to know, this is just a critical number question. Find critical numbers. So if we want to know the critical numbers, let's find where the derivative pieces equal 0 or where the derivative is undefined. So if I take the derivative of the pieces, I have a 2x and I have a negative 2x. And if I figure out where both of those are 0, they both produce a critical number of 0. Like 0 is the number that makes them 0. So 0 is a critical number. There's no other values of the derivative. Like there's no other numbers that would make the derivative 0 besides 0. 0 is in the domain of the original function, so we're good with that aspect. And then the only thing else to consider is this 1, this split at 1. I mean, visually we saw the graph, it's not differentiable there, so the derivative does not exist there. So 1 is also going to be a critical number because of the fact that it's not even continuous there. If it's not continuous, you can't take the derivative. The other thing that you consider would be the fact that if you looked at that split of 1 with the derivative, the 1 from the left piece and the derivative of 1 from the right piece, in one of them you get 2 and the other you get -2, and these are not the same. So I mean the slopes of the tangent lines wouldn't have even been the same. But at 1 it's not continuous. So it's not differentiable. And again, that makes it a critical number. I mean, there's a split there. There's not much you can do with it. But the question that you'll be asked is, what are the critical numbers? So your job is to be able to find where the derivative is 0 and then consider where they split in the domain. Because odds are it's a critical number if you need to. But I think, like I said, there were 2 questions. It's not that big of a thing for this. But it showed up in the homework. Okay, how are we doing? We're doing good? Good on time, 7 minutes. So again, the majority of that homework from section 4.2 just has you do, it has you do critical numbers, it has you do absolute max, absolute min, and so your job is going to be the derivative, finding where the derivative is 0, revisiting your derivative rules with power functions, with square roots, radicals. I think I saw a logarithm show up somewhere, like a natural log derivative, which we did them in chapter 3. So if you need to get back out that derivative to know sheet, I don't remember where I put oh, that's not your class. Let me come back to this. Go back and look at them. I mean, you have all the resources in the world you could want from your home at your computer. So you could just look at them. So with the time we have left, section 3, I'm just going to pop this up because this is something that I did last semester, and I'm going to post these on As You Learn too, so you can go ahead and look at them. So 4.3 is called the mean value theorem, but I'm not going to cover the mean. It's in there. It talks about a function being continuous. It talks about it being differentiable, and then it looks at slopes of tangent lines being parallel. So the bulk of section 4.3 comes from using this increasing and decreasing test, which is what we're going to focus on. So if you want to read about the mean value theorem, you can, but I'm not covering it. 4.4 is going to look at minimums and maximums locally, concave up, concave down, and then 4.6 sort of ties it all together. So that's what those are grouped together in homework. That's let's say Tuesday. We might get to 4.6 by Thursday. I don't really know. But what we're using in section 4.3 is this increasing, decreasing function test. And we've looked at it before. It just wasn't called this. We've looked at a function. We've looked at the graph of its derivative. And basically, if you have a function that's derivative, that has a derivative, it's differentiable. Wherever the derivative is positive, that's where the function increases. Wherever the derivative is negative, that's where the function decreases. We've seen this before. Like I've given you a picture of a function and you've had to tie it and you had to match it to the graph of the derivative. Maybe you remember it was a handout. But you have to be able to find the critical numbers and then sort of test in between them. So, but I can leave this up if you want me to. It's called the first derivative. It's a first derivative test or an increasing, decreasing function test, I think is what your book actually calls it. But it's using the first derivative to figure out where the function increases and decreases. Now, I realize you could look at it, like I'm gonna do this graph, we'll do this function. And I'll bring it back up here in a second, because I think some of you are probably copying it. 2x cubed, where did that go? Minus 9x squared plus 12x plus 5. So I'm pretty sure that a lot of you see if I can screenshot this and write on it. If this will work in here. Yeah, a little bit. This part of the graph is increasing up to that maximum point. This little part of the graph is decreasing. Okay. I got like 5 minutes. Okay, that's fine. That's decreasing to this point, and then after the graph, it's increasing. I think visually you can see that, but you have to be able to report the exact intervals that that function increases and decreases. And sometimes it's like 1 to 2 and 3 to infinity. And sometimes it's like the square root of 15 over 2 to infinity. So you have to be exact, and we're going to use calculus to help us do that. But we're going to figure out from the first derivative intervals where the graph of a function increases and decreases without really looking at the graph. You can look at the graph if you need to, but it's not going to be necessary. So that's sort of where we're headed with this. And if I did this particular function, that's the one that I just wrote. 2x cubed minus 9x squared plus 12x plus 5. So the first thing you have to do is find the critical numbers. And then once you find the derivative, and once you find the derivative, find what equals 0 and get the critical numbers. So this is done in section 2, preps you for section 3. And this is where, again, we're going to find the derivative, we're going to find the critical numbers, and then we're going to look, just to preview this, we'll do, I like to make these little charts, and some of you that have had calculus before, maybe you remember this, but you sort of take your critical numbers of 2 and 1, and you look below, in between, above, and see if the derivative is positive or negative. You don't even need what it is, you just need whether it's positive or negative, and it'll tell you where the function increases or decreases. But I think we'll save that for tomorrow and let you, I can post these if you want to preview them before we have class tomorrow. I have them if you want to look at them. And like I said, this has been recorded, so I can post it if you need to go back and look at it. But if you haven't done the 3.5, the linear approximation, do that because it shuts off soon. And then go ahead and start the extrema, the min, the max, as soon as you possibly can, because you need to. Don't drag your feet. I don't know how else to say that. The quicker you do this, as we talk about it from class, it's just like when we would meet for lecture. You have less distractions at home now than you did before. In your life, I hope you have less. I don't know, maybe you have more, who knows. I had a colleague said they had somebody bouncing a baby while they were doing a Zoom session. I'm like, no. I've had animals. I've seen the animals. That's all I've seen so far, the cats and the dogs. But you let me know if you have questions. And like I said, office hours, math lab, we'll make this work, but the effort's on you. You have to try the homework. You need to figure out if you understand the material. If you need to rewatch this lecture, give me like 10 to 30 minutes, maybe, depending on life, and I'll try to upload it. So if you need to rewatch it, you can. But like I said, if you need to meet with me or ask questions, haven't scanned your tests, but that's a goal. Maybe I can do that some this weekend, and we can talk about that. But does anybody have questions? No. I can only see a few of you. So, okay. Well, we'll go. You go and you do the math things and the life things, and stay healthy, and I'll see you tomorrow. Bye. Oh, I got some thumbs up and some clap hands.
Puckett, are you gonna post the Zoom sessions?
I did. I posted this one from yesterday. Did you see them?
Okay, I just wanted to make sure that this one was gonna be posted because I wasn't here for some of it. I had to leave the room.
Yeah, no, as soon as I hit end meeting, it'll stop recording, and it takes a few minutes to turn into an MP4 video file, and then it takes a few minutes to load it in As You Learn. So that's why it's like, give me about a half hour or so, and I'll try to have it posted.
All right, thank you so much.
You're welcome.